Tonight, we journey beyond the edge of everything you've ever known, into a place where time itself begins to lose meaning, where space stretches so infinitely that distance becomes almost incomprehensible. We're traveling to the heart of the universe's darkest mystery, a cosmic entity so massive, so impossibly immense, that it exists almost as a monument to the fundamental powers that govern all existence. Its name is TON 618, and as you settle into the quietness of this moment, we're going to explore what it means for something to be so incredibly, almost unimaginably large that the human mind can barely grasp the magnitude of its being. But before we venture too deeply into those cosmic waters, I want you to know that you're exactly where you need to be right now. Perhaps you've had a long day. Perhaps your mind has been racing. Or perhaps you simply want to feel small for a moment, to remember that you are part of something far greater than any worry or concern that might be occupying your thoughts. So settle in, get comfortable, and let the universe whisper its secrets to you tonight. There's no rush here. We have all the time in the world, and time, as you'll come to understand, is one of the most precious things we can explore together. Let's begin with a simple question. What is size, really? We live in a world of measurable things. We know the height of a building, the distance to the horizon, the width of an ocean. But when we venture into the cosmos, our measurements begin to feel increasingly inadequate. The mind, which evolved to understand distances of a few hundred meters and weights we could hold in our hands, suddenly finds itself grasping for concepts that stretch beyond its natural capabilities. And yet, there's a beautiful comfort in that incomprehensibility, isn't there? When something is too large to fully understand, it becomes almost peaceful. It becomes transcendent. TON 618 is one such object. It is a black hole, but not merely a black hole. It is a supermassive black hole. And when we say supermassive, we need to understand that we are using the word supermassive in a way that almost mocks itself. Because TON 618 is so enormously, impossibly massive, that calling it supermassive feels almost like an understatement, like calling the ocean wet or the sky big. The truth is that our language sometimes fails us when confronted with the most extreme objects in the universe, but we'll do our best to paint a picture with words tonight. Imagine, if you will, standing on the surface of our Earth. Beneath your feet lies a world that has taken billions of years to form, a sphere of rock and metal and water that spans nearly 13,000 kilometers from pole to pole. This is our home, and it feels immensely large to us. From any point on Earth's surface, the horizon stretches seemingly forever. Yet our entire planet, with all its mountains and oceans and continents and deserts, fits into space with countless other worlds. And beyond those worlds lies our sun, a star so massive that 1.3 million Earths could fit inside it, a ball of plasma and light that has been burning for nearly 5 billion years and will burn for billions more. Our sun, which dwarfs our world by such an incomprehensible margin, is itself utterly insignificant compared to the objects we're about to discuss. You see, our sun's gravity holds our entire planetary system in place. Yet the gravity of our sun is weak, almost negligible, when compared to what we find at the centers of galaxies, where something far stranger dwells. At the heart of most large galaxies, and perhaps all of them, we're still learning, there exists a supermassive black hole. These objects are so gravitationally intense that nothing, not even light itself, can escape once it crosses a certain point of no return. That point is called the event horizon, and it marks the boundary between the observable universe and a region from which no information, no particles, no waves of light can ever return to tell us what happens within. Black holes exist in a kind of cosmic isolation, forever separated from the rest of the universe by a boundary so absolute that even our most powerful telescopes cannot penetrate it. But here's where our journey becomes truly fascinating. Not all black holes are equally massive. Some are stellar mass black holes, created when massive stars collapse at the end of their lives. These objects might weigh as much as 10 or 20 suns, and they would be considered enormous by any reasonable standard. Yet compared to the supermassive black holes that lurk at the centers of galaxies, they are almost quaint, almost gentle. There is a difference between scales that is itself almost impossible to comprehend, a hierarchy of size that plays out across the universe in ways we are only beginning to understand. And TON 618 sits at an extreme point on this hierarchy. It is not merely a large supermassive black hole. It is one of the largest known objects of its kind. When astronomers first detected it, when they began to measure its mass and understand its scale, they did so with a mixture of awe and something approaching disbelief. How could something be so large? How could gravity concentrate so much mass into a single point? And as we venture deeper into this night, as we explore what it would mean to encounter such an object, perhaps we'll begin to feel that same awe, that same sense of being humbled by the sheer scale of creation. The story of TON 618, like many profound discoveries in astronomy, begins with human curiosity and human ingenuity. It begins with people looking at the night sky and wondering not just what they were seeing, but how to see more clearly. In the 1950s and 1960s, as telescopes became more sophisticated and as our ability to detect different types of radiation improved, astronomers began noticing something strange. Some objects that appeared to be stars, or seemed to be stars when viewed through a conventional telescope, were behaving in extraordinary ways. They were emitting vast amounts of energy, far more than any normal star should emit. They were producing radio waves and X-rays and visible light in patterns that didn't match anything astronomers had seen before. These objects became known as quasars, a name derived from quasi-stellar radio source, because they looked like stars, but radiated like nothing anyone had ever encountered. The discovery of quasars was one of the great revolutions in astronomy, as profound in its way as Galileo's first glimpse through a telescope. Suddenly, astronomers realized that the universe was far more violent, far more energetic, and far more interesting than anyone had previously imagined. The question that drove many astronomers in those days was, what could possibly be generating such immense amounts of energy? The answer, though it took many years of observation and calculation to fully understand, was black holes. At the heart of these quasars, feeding on infalling material, spinning at nearly the speed of light, were supermassive black holes. As material spiraled inward toward the event horizon, it accelerated to relativistic speeds. The friction and the collisions and the release of gravitational potential energy all combined to create jets of radiation that shot outward from the black hole at nearly the speed of light. These jets, millions of light years long, could outshine entire galaxies of stars. They were, in essence, the universe's most powerful engines. TON 618 is one such quasar. The designation, TON 618, comes from a catalog of astronomical objects, a naming convention that tells us this was discovered and cataloged as part of a systematic survey. But when we look up TON 618 in those catalogs, when we examine the data collected by telescopes across decades, we begin to understand what we are looking at, the most luminous quasar that has ever been observed. TON 618 is shining with the light of nearly 100 trillion suns, a brightness so staggering that even from a distance of 18 billion light years, meaning we are seeing it as it was 18 billion years ago, when the universe was itself younger and stranger, it still stands out as one of the most brilliant objects in the cosmos. And at the heart of that brilliance, at the center of that unimaginable radiative power, spins a black hole whose mass is estimated at between 40 billion and 66 billion times the mass of our Sun. To put this in perspective, the supermassive black hole at the center of our own galaxy, Sagittarius A star, has a mass of roughly 4 million suns. TON 618's black hole is more than 10,000 times more massive. It is not merely larger. It exists in a different category of size entirely. Imagine for a moment that we could somehow scale down the comparison to something more relatable. If Sagittarius, a star, were the size of a golf ball, already enormous, already incomprehensible, then Ton 618 would be a sphere roughly the size of a mountain. The size difference would be so vast that looking at one next to the other would almost hurt the mind. Yet these are both black holes. These are both objects that have been created by similar processes, that follow the same physical laws, and yet they differ in scale by a factor that staggers the imagination. But what does this mass actually mean? How do we translate these numbers into something we can almost feel, almost sense? Let's think about the event horizon, that invisible boundary beyond which nothing returns. For our sun, which has a mass of roughly 2 times 10 to the 30th kilograms, the event horizon would be only about 3 kilometers in radius. The sun could be crushed down to a black hole smaller than a city. For Ton 618, with its billions of times more mass, the event horizon is vastly larger. The event horizon of Ton 618 is estimated to be roughly 130 billion kilometers in radius. That means the event horizon alone is larger than our entire solar system. To put this another way, if you could somehow travel in a straight line from Ton 618's event horizon to the black hole at its center, you would traverse a distance of 130 billion kilometers. The distance from the Sun to Neptune is only about 5 billion kilometers. Let that sink in for a moment. The region from which no light can escape is so large that the Sun could orbit within it, billions of kilometers from the center. The interior of that black hole, that region of infinite density and broken space and time, is separated from the edge by a distance greater than the span of our planetary system. And yet, to an outside observer, all that immensity, all that mass, all that power is concentrated at a single point, invisible and absolute. As we settle further into this exploration tonight, I want you to imagine standing at the event horizon of Ton 618. Of course, in reality, you could never do this. The tidal forces would destroy you, the radiation would incinerate you, and you would be pulled inexorably into the black hole. But in imagination, in this peaceful realm of thought, you can stand there safely and observe. The event horizon would stretch out before you in every direction. Behind you, the universe would continue, indifferent to your presence. But ahead of you, beyond that horizon, there would be nothing. Not darkness, exactly, but an absence of information, a boundary between existence as you know it and something utterly beyond comprehension. The mathematics of black holes tell us that at the center of Ton 618, space itself becomes infinitely curved. There is a singularity, a point where density becomes infinite and our equations break down. General relativity, Einstein's magnificent description of gravity and the curvature of space-time, ceases to be applicable. We simply don't know what happens there, whether the singularity is truly a point, or whether quantum mechanics, a physics we don't yet fully understand, modifies what we think we know. It is one of the great mysteries remaining in physics, a mystery that sits at the very heart of one of the universe's most extreme objects. And this is where Ton 618 becomes not merely large, but philosophically intriguing. Here's an object so massive, so gravity-warped, so utterly extreme that it represents the ultimate limits of the universe as we understand it. To study Ton 618 is to study a place where our best science reaches its limits, where theory and observation meet at the frontier of human knowledge. It is a place that reminds us of how young our civilization truly is, how much we still don't understand, and how vast and strange the cosmos truly is. But there's something even more profound than the sheer size of Ton 618, and that something involves time itself. You see, when we think about this black hole in the context of Einstein's relativity, a theory that shows us how space and time are woven together into a single fabric, we realize that at the event horizon, something extraordinary happens to time. Time, that constant river that flows inexorably forward in our daily experience, begins to slow down relative to outside observers. If you were watching someone fall toward the event horizon of ton 618, you would see them move more and more slowly. They would appear to freeze at the event horizon, their image becoming dimmer and dimmer until it faded to invisibility. And yet, from their own perspective, they would cross the event horizon almost normally, completely unaware of anything unusual happening at that particular moment. This is not science fiction. This is what Einstein's mathematics tells us about the nature of gravity and the curvature of spacetime. This is reality at its most profound. Time flows differently in different places. The faster you move, the more slowly time passes for you relative to someone moving slower. The stronger the gravity around you, the more slowly time passes. At the event horizon of a black hole, time and space have become so warped, so curved, so profoundly altered by the immense gravity that the very concepts we use in our everyday experience begin to lose all meaning. Imagine for a moment what it would be like to experience such a place. Imagine being in a ship, falling slowly toward ton 618. At first, nothing would seem particularly different. But as you descended closer and closer, you would begin to notice effects that would become increasingly strange. Tidal forces would become important. The gravity pulling on the parts of your ship closest to the black hole would be significantly stronger than the gravity pulling on the more distant parts. Eventually, these tidal forces would become so severe that they would stretch you and your ship and everything you had brought with you into long, thin strands. Astronomers call this process spaghettification, a term that sounds almost whimsical, but describes something quite horrifying. But before you reached that point, before the tidal forces became catastrophic, you would notice something else. Time would seem to slow down around you. Your instruments would tell you that time was passing normally, at its usual rate. But if you could somehow look outward toward the universe, if you could see the stars and galaxies beyond, you would notice that everything out there seemed to be moving faster. Centuries would pass in the outside universe for every second that passed for you. You would watch the far future of the cosmos unfold and fast forward, centuries and millennia occurring in the blink of an eye, all while you slowly descended into regions of space and time so warped that all our knowledge begins to break down. This temporal dilation, this warping of time itself by gravity, is one of the most profound consequences of Einstein's theory of general relativity. It is not merely a theoretical curiosity. Time dilation is something we have measured and verified many times. Precise atomic clocks move to different altitudes on Earth, tick at different rates. Particles traveling at relativistic speeds live longer than stationary particles because time passes more slowly for them. The satellites in the GPS system have to account for relativistic time dilation, or they would quickly become useless for navigation. The universe is not indifferent to time, is a property of the universe itself, woven together with space into a fabric that curves and warps and bends in response to mass and energy. And at ton 618, at the heart of that vast black hole, the warping of time and space reaches extremes that are almost impossible to comprehend. Not only is the black hole incredibly massive, not only does it possess gravity so strong that nothing can escape its pull, but it also exists in a state where the very foundation of reality, space and time themselves, has become alien and strange. Now, imagine if you will that we could somehow journey safely through this cosmic environment, protected by some advanced technology we can only dream of. Imagine that we could observe ton 618 from various distances, getting gradually closer while remaining safe from its destructive effects. As we approached, we would begin to see phenomena that would seem increasingly bizarre. There are regions around ton 618 where the infalling material becomes so hot and collides so violently that it emits powerful jets of radiation. These jets, accelerated by the black hole's intense gravity and its powerful magnetic fields, shoot outward at nearly the speed of light. From our vantage point, we would see beams of light and radiation and energetic particles creating a cosmic display of unimaginable power. These jets extend for millions of light years across space. They would dwarf any galaxies they passed through. They would reshape the cosmic environment they encountered. But there's something even more intriguing that occurs closer to the black hole itself. Very near the event horizon, in a region called the accretion disk, material orbits at nearly the speed of light. The disk becomes incredibly hot, millions of degrees. Atoms are stripped of their electrons. The magnetic fields generated by the spinning black hole become so intense that they can influence the motion of charged particles millions of kilometers away. Shocks form where different streams of infalling material collide. All of this occurs in a region that, while enormous by human standards, is actually quite small compared to the scale of galaxies or even solar systems. This is where the universe shows us some of its deepest secrets. This is where gravity reigns supreme. This is where physics reaches its most extreme and most profound states. Slowly, gently, I want you to take a journey with me now. We're not actually going to approach TON 618. That would be neither safe nor pleasant, but we're going to take a mental journey, scaling up and down the sizes of things to help you begin to grasp the almost incomprehensible magnitude of what we're discussing. Let's start small. Start with something familiar. A human being. You, as you sit here listening to this, are roughly 2 meters tall. You can hold something in your hand, a pen, a stone, a piece of fruit, and the size of that object is something your brain can immediately grasp. These are the scales at which evolution shaped your perceptions. Your ancestors hunted and gathered and lived in a world where distances were measured in meters and tens of meters. Your eyes and your brain developed to make sense of that scale. But now let's expand. Imagine you could zoom out and see a city from above. A large city might span several dozen kilometers across. If you were in a high-altitude aircraft, you could see the entire city in a single view, though it would be difficult to make out details. Keep zooming out. A country. A continent. The Earth itself. A sphere of rock and water and air, about 13,000 kilometers in diameter, rotating slowly in space. If you were standing on the moon and looking at Earth, it would appear as a beautiful blue and white sphere, smaller than a coin held at arm's length. And yet, the entire history of human civilization, every war ever fought, every city ever built, every life ever lived, has occurred on the surface of that small sphere. But Earth, vast as it seems to us, is small compared to our sun. The sun is 109 times wider than Earth. If Earth were a marble, the sun would be a sphere roughly the size of a large beach ball. The sun contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets, is just a tiny fraction of the sun's mass. Now let's zoom out further. Our solar system spans roughly 40 billion kilometers across, from the sun to the outermost reaches of the Oort cloud, where comets originate. That's a distance that light, the fastest thing we know, takes many months to traverse. And yet, our sun is just one star among hundreds of billions of stars in our galaxy, the Milky Way. If the sun were a grain of sand, our galaxy would be a beach spanning the entire world, with billions upon billions of grains. The Milky Way itself is nearly 100,000 light years across. A light year is the distance that light travels in 1 year, moving at a speed of roughly 300,000 kilometers per second. It's hard to grasp what a light year even means. If you drove a car at 100 kilometers per hour, it would take you 30 million years to travel 1 light year. Our entire galaxy, from one side to the other, is 100,000 of those impossibly vast distances. It would take light itself 100,000 years to cross our galaxy. And our galaxy is just one galaxy among perhaps 2 trillion galaxies in the observable universe. If you could somehow zoom out to see all the galaxies, they would form a cosmic web, with vast sheets and filaments of galaxies separated by enormous voids. The universe as we know It extends 93 billion light-years from edge to edge, the observable universe, at least. We don't know if there's more beyond what we can see. In the center of our galaxy, there is a supermassive black hole called Sagittarius A star. It has a mass of roughly 4 million times the mass of our Sun. That is incomprehensibly massive. The event horizon of Sagittarius A star is roughly 40 million kilometers in diameter. Our entire Earth, orbiting our Sun, would fit inside that event horizon billions of times over. And yet, Sagittarius A star is small compared to TON 618. TON 618's black hole has a mass of between 40 and 66 billion solar masses. It is 10 to 15,000 times more massive than Sagittarius A star. The event horizon is roughly 260 billion kilometers in diameter, 4 times larger than the event horizon of Sagittarius A star. No, wait, if the mass is 10,000 times larger, and the event horizon scales with mass, then the event horizon should be 10,000 times larger in linear size. Actually, the mathematics is a bit more subtle. The radius of an event horizon is proportional to the mass of the black hole. If you increase the mass by a factor of 10,000, the radius of the event horizon increases by the same factor of 10,000. So the event horizon of TON 618 is approximately 130 billion kilometers in radius. That means the diameter of the event horizon is roughly 260 billion kilometers. The distance from the Sun to Neptune, Neptune being the outermost planet in our solar system, is only about 5 billion kilometers. So the event horizon of TON 618, the boundary beyond which nothing can escape, is 50 times larger than the entire orbit of Neptune. Our entire solar system, from the Sun to the outermost reaches of the known planetary orbits, could fit inside that event horizon with room to spare. Picture this in your mind. Here is the Sun, burning and radiating energy into space. Around it, at vast distances, orbit 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. It takes light 8 minutes to travel from the Sun to Earth. It takes light hours to reach Neptune. And all of this, the entire planetary system of our Sun, in all its vastness, would fit easily inside the event horizon of TON 618, with enough room that additional solar systems could orbit within that same cosmic boundary. But remember, the event horizon is not the material of the black hole. It's a boundary, a geometrical feature of space-time itself. The actual singularity, the point where all the mass is concentrated, would be at the center. The distance from the event horizon to the singularity of TON 618 would be 130 billion kilometers. That means if you started at the edge of the event horizon and traveled straight toward the center, you would need to journey across a distance greater than the distance from the Sun to Neptune, just to reach the singularity. And here is where the mind truly begins to struggle, because that singularity, that infinitely dense point of matter, contains the mass of 40 to 66 billion suns. Let me say that again, more slowly. A single point, a dimensionless singularity at the center of TON 618, contains more mass than 40 billion suns, each of which is 109 times more massive than Earth. This is a concentration of matter that is so extreme, so profound, that it breaks the laws of physics as we understand them. At the singularity, density is infinite. Space and time lose all meaning. Our equations fail us. We reach the boundary of human knowledge. And yet, we know that these singularities exist. We have observed their effects. We have measured the gravity they produce. Somewhere in the universe, TON 618 is spinning, radiating energy, and at its heart sits this impossible concentration of matter. Now, let's talk about what happens when we approach understanding the extreme. Physics around TON 618. Most of the physics that governs the region near a black hole is well understood. We use Einstein's theory of general relativity, which describes gravity as the curvature of spacetime caused by mass and energy. This theory is extraordinarily successful. It has been tested in countless ways, in different regimes, under different conditions, and it has been proven correct again and again. But there's a region where general relativity begins to break down, and that region is inside the singularity of a black hole. You see, general relativity is a classical theory. It doesn't account for quantum mechanics, the strange probabilistic physics that governs the subatomic world. And at the singularity, where density is infinite and space and time are infinitely curved, quantum effects should become important. In fact, they should become dominant. But we don't have a complete theory of quantum gravity. We don't fully understand how to combine the geometry of general relativity with the probabilistic nature of quantum mechanics. This is perhaps the most profound unsolved problem in physics. For decades, physicists have been trying to develop a theory of quantum gravity. Some have worked on string theory, which proposes that the fundamental building blocks of reality are not particles, but tiny vibrating strings. Others have worked on loop quantum gravity, which tries to quantize spacetime itself, treating it not as a smooth continuum, but as a granular structure made up of tiny loops of geometry. Still others have explored other approaches, each with its own merits and challenges. But what we can say with confidence is that inside a black hole, near the singularity, the laws of physics as we know them cease to apply. This is profoundly humbling. Here is a place in the universe, a real place, not a theoretical abstraction, where our best science cannot explain what is happening. TON 618 singularity is a monument to the limits of human knowledge. Outside the singularity, though, things are a bit better understood. In the region between the event horizon and the singularity, general relativity still applies, and we can use it to understand the physics. This region is governed entirely by gravity. Particles that venture into this region are subject to tidal forces that would tear them apart long before they reach the singularity. The curvature of spacetime is so severe that it dominates everything. But even more interesting than the region inside the event horizon is the region immediately outside it. At the event horizon itself, something extraordinary happens. Light, traveling at its maximum possible speed, follows a path that orbits the event horizon without ever falling in, and without ever escaping to infinity. It's a state of equilibrium, a kind of cosmic knife edge between two fates. Anything moving even slightly slower than the speed of light will eventually fall in. Anything moving even slightly faster will eventually escape to infinity. But light itself, photons of pure energy, can orbit the event horizon eternally, trapped in a kind of photon sphere, invisible to any external observer. Just outside the event horizon, in the region where matter isn't falling toward the black hole, we find the accretion disk. This is where the action happens, where the gravitational potential energy of infalling material is released in the form of heat and radiation. The accretion disk of a black hole can shine with the light of billions of stars. In the case of TON 618, the accretion disk is so luminous that from a distance of 18 billion light-years, it outshines entire galaxies. The material in the accretion disk moves at relativistic speeds. It forms shock fronts and turbulent regions where energy is released in the form of heat. Electrons are accelerated to tremendous speeds, moving at a significant fraction of the speed of light. These rapidly moving electrons interact with magnetic fields, and when charged particles move through magnetic fields, they emit radiation. This radiation includes visible light, ultraviolet light, X-rays, and gamma rays. The disk becomes incredibly hot, millions of degrees, and this heat is radiated away into space. This is how the gravitational potential energy of the infalling material is converted into the incredible brightness we observe. At the same time, the spinning black hole generates tremendous magnetic fields. These fields become amplified by the motion of the conducting plasma in the accretion disk. The magnetic fields become so strong that they can actually hold back the infalling material, creating jets that shoot outward at nearly the speed of light. These jets are among the most energetic phenomena in the universe. In the case of TON 618, the jets extend for millions of light years. If you could somehow see the entire structure, from the inner accretion disk to the outer jets, you would be looking at an object that spans a region larger than many galaxy clusters. But this complexity, this richness of physics, all occurs at the periphery of TON 618. At the center sits the singularity, incomprehensible and absolute, a reminder that there are places in the universe where our understanding reaches its limits. And yet, and this is something that should fill you with wonder, even as it humbles you, we have learned all of this through observation and calculation. Humans, living on a small planet orbiting a small star, have used our intelligence and our instruments to understand the most extreme objects in the universe. We have used telescopes and radio arrays and satellite observatories to gather light and radiation from TON 618 and other objects like it. We have used the laws of physics to interpret that radiation and understand what we're looking at. This is one of the greatest achievements of human civilization. Whatever our limitations, whatever we don't yet understand, we have managed to extend our perception across billions of light years and comprehend the nature of the cosmos. Let me take you on a journey now through time and light, because understanding TON 618 requires us to think about not just space, but also the history of the universe itself. When we observe TON 618, we are not seeing it as it is now. We are seeing it as it was in the past. TON 618 is about 18 billion light-years away. That means the light we receive from it has been traveling for 18 billion years. The universe itself is only about 13.8 billion years old. So what we're seeing is TON 618, as it was when the universe was very young, during a time called the Epoch of Reionization, when the first galaxies were forming and the universe was still filling with light. This leads us to a profound question. How did such a massive black hole come to exist so early in the universe's history? Our current understanding of black hole formation suggests that black holes grow by feeding on material and by merging with other black holes. A supermassive black hole can grow from a smaller seed by consuming material and gradually accumulating mass. But for TON 618 to reach its current mass of 40 to 66 billion solar masses in the time since the Big Bang, it would have had to grow extraordinarily rapidly. The timescale seems almost impossible, unless there's something about the formation of the first black holes that we don't yet understand. This is one of the great mysteries of modern astrophysics. The existence of such massive black holes so early in the universe's history suggests that either our understanding of how black holes grow is incomplete, or the initial conditions of the universe were different from what we think, or there's some process we haven't yet discovered. TON 618 and other ultramassive black holes observed at great distances challenge our current models and push us to develop new understanding. Imagine for a moment the universe as it was when TON 618 was shining with maximum brightness. The universe was much denser then. The first stars had formed, and in many places they had died and collapsed into black holes. The intergalactic gas was still being heated and shaped by radiation from the first quasars. The universe was a far more violent, far more energetic place than it is today. And in the midst of all that cosmic turmoil, TON 618 was there, shining with the light of 100 trillion suns, an enormous beacon in the young universe. The light from TON 618 traveled across the expanding universe for 18 billion years. During all that time, the universe was expanding, stretching, and growing. The expansion of space itself stretched the light waves, making them redder, lower in frequency. This process is called cosmological redshift, and it's one of the key ways we measure distances to distant objects. The more redshifted the light, the more distant the object, because the more space expansion has occurred since the light was emitted. And then, after 18 billion years of traveling through the cosmos, that ancient light reached Earth, Some of it was detected by our telescopes. It was analyzed and catalogued and studied. And from that study, astronomers deduced the presence of one of the most extreme objects in the universe. But remember, while we were seeing light that was 18 billion years old, Ton 618 itself had continued to exist. The black hole has aged another few billion years. We don't know if it's still as luminous as it was when we're seeing it. We don't know if the material supply around it has changed. We're seeing only a snapshot from the ancient past. TON 618, as it truly is now, at this very moment, might be completely different. But we have no way of knowing, because we cannot receive light from it that has traveled less time than 18 billion years. In a very real sense, Ton 618, as we observe it, is a ghost, a phantom image of something that existed long ago. This is something to contemplate as we journey through the night. Every distant object we observe in astronomy is a message from the past. The further away something is, the further back in time we're seeing. When we look at the most distant galaxies, we're seeing the universe as it was over 13 billion years ago, just a few 100 million years after the Big Bang. Our telescopes are time machines, in a sense. They allow us to look backward through cosmic history and see how the universe has evolved. And Ton 618 is one of these time machines, showing us a moment when the universe was young and filled with the light of brilliant quasars. Now, having journeyed through the physics and the history, let's revisit the scales one more time, because comparison is the only tool we truly have to understand vastness. Let me ask you something. Imagine you held a golf ball in your hand. You could see it clearly, touch it, understand its shape and size. Now imagine someone gave you a sphere the size of Earth. Could you grasp it? Could you hold it? Obviously not. The difference between those two objects is a factor of roughly 40 billion. The diameter of Earth is about 12,742 kilometers. The diameter of a golf ball is about 4.3 centimeters. If you divide the Earth's diameter by the golf ball's diameter, you get about 296 billion. So actually, the golf ball is even smaller compared to Earth than I said. Now, imagine you could somehow scale Ton 618's event horizon down to a golf ball. How much would the singularity be scaled down? Well, they'd both scale by the same factor. If you reduce the event horizon from 260 billion kilometers to 4.3 centimeters, you'd be scaling down by a factor of about 6 times 10 to the 12th. And the singularity, being infinitely dense, would still be infinitely dense in your scaled-down version. The singularity is dimensionless. It's a single point, so no matter how much you scale the rest of the black hole, the singularity remains a point. This reveals something profound about black holes. They are not like ordinary objects. You can't simply scale them down and have them behave in a miniature way. The singularity remains incomprehensibly dense no matter what. If you could actually create a miniature black hole the size of a golf ball, it would have properties that are just as alien and just as extreme as Ton 618. It would have an event horizon just as absolute. It would have a singularity at its center, just as infinitely curved. But beyond the mathematics, let me try a different kind of comparison. The event horizon of Ton 618 is 260 billion kilometers in diameter. The distance from Earth to the Sun is 150 million kilometers. So the event horizon of Ton 618 is about 1,700 times larger than the distance from Earth to the Sun. If you place the Sun at the center and the Earth in its orbit 150 million kilometers away, the Earth would be nowhere near the edge of Ton 618's event horizon. The Earth would be just barely inside, orbiting in a region where the space is so warped by gravity that time itself flows strangely. Imagine a solar system orbiting inside the event horizon of Ton 618. The sun would shine, planets would orbit, life might even evolve, all completely unaware that their entire universe was contained within the event horizon of this unimaginably massive black hole. They would have no way of knowing, because light cannot escape from the event horizon. From their perspective, they would be in a universe as complete and real as our own. But the inhabitants of that hidden solar system would eventually discover something strange. Their space, their universe, would begin to contract around them. The event horizon would approach, and eventually, inevitably, everything would fall toward the singularity. Time would slow down as they approached. The outside universe would age billions of years while they experienced only seconds. And then, finally, they would cross the point of no return, and whatever happened inside the event horizon, whatever fate befell them, would be forever hidden from any observer outside. This is not just speculation. This is what the mathematics of general relativity tells us about the nature of black holes and the inevitable fate of anything that ventures too close. Let's now discuss something that might seem counterintuitive. Black holes radiate. They glow. They emit light. How can something that is defined by the fact that nothing can escape from it possibly emit light? The answer lies in quantum mechanics, in the probabilistic nature of the subatomic world. In 1974, Stephen Hawking made a remarkable discovery. He showed that quantum effects near the event horizon of a black hole could lead to the emission of radiation. The vacuum of space, according to quantum mechanics, is not truly empty. It is constantly seething with virtual particles and antiparticles that appear and disappear in pairs. Near the event horizon of a black hole, something extraordinary can happen. One of these virtual particle-antiparticle pairs can be created such that one particle falls into the black hole while the other escapes to infinity. From the perspective of an outside observer, it looks as though the black hole is emitting radiation. This process is called Hawking radiation, and it has profound consequences. It means that black holes are not perfectly black. They emit radiation, and as they emit radiation, they lose energy. They evaporate. A small black hole would evaporate very quickly, emitting radiation with increasingly high energy as it shrinks. But a large black hole would evaporate very slowly. TON 618, with its enormous mass of 40 to 66 billion suns, would evaporate so slowly that the lifetime would be incomprehensibly long. To give you an idea of the time scale, the evaporation lifetime of a supermassive black hole like TON 618 would be something like 10,100 years, or 10 to the 100th power years. That's a number with 100 zeros after it. The current age of the universe is only about YY years, or 10 billion years. To put this in perspective, if you waited 10,100 years, you could write down the number 1, followed by 100 zeros. If you printed that in the smallest possible font, on the largest possible sheet of paper, using the smallest possible print, you would need a sheet of paper that spanned the entire observable universe, many times over, just to write down the number of years it would take for TON 618 to completely evaporate. And yet, from a theoretical perspective, TON 618 is evaporating right now. Even as it shines with the light of trillions of suns, it is also quietly, imperceptibly, emitting Hawking radiation. It is losing energy, bit by infinitesimal bit. But at its current rate, it would take longer than the age of the universe, multiplied by itself countless times, before the effect became noticeable. For all practical purposes, TON 618 is eternal. It will outlast the stars. It will outlast galaxies. It will outlast the age of stellar nucleosynthesis, when the universe is so old that new stars will no longer form. It will be there in the far, far future, when the last stars have burned out and the universe is filled with cold, dark remnants. But the Hawking radiation emission does reveal something beautiful about the universe. Black holes are not separate from the rest of physics. They're not isolated exceptions. They're intimately connected to quantum mechanics and thermodynamics. A black hole has a temperature, a concept that at first seems bizarre when applied to an object from which nothing can escape. But the mathematical structure of general relativity and quantum mechanics together imply that a black hole's event horizon behaves like a thermal surface, radiating energy at a temperature inversely proportional to its mass. For Ton 618, this temperature would be extraordinarily low, just a fraction of a degree above absolute zero. At such a low temperature, the Hawking radiation would be extremely weak and difficult to detect. But it's there, nonetheless, a quantum whisper from the edge of absolute gravity, a reminder that the universe operates according to principles that are elegant and unified, even if we don't yet fully understand them. As we approach the deeper part of our night journey, let's allow ourselves to contemplate what Ton 618 means not just scientifically, but philosophically. What does it mean to exist in a universe that contains such extreme objects? What does it mean that our minds, evolved on a small planet to understand the scale of meters and seconds, have managed to comprehend something so vast? There is something almost sublime about black holes, in the original sense of the word sublime. Sublimity is the experience of confronting something so vast, so powerful, so beyond human scale that it exceeds our capacity to fully comprehend it, yet we are compelled to try. Standing before a massive mountain, watching a storm rage across the sky, contemplating the depth of the ocean, these are experiences of sublimity. And contemplating Ton 618, with its impossible vastness and its absolute gravity, is perhaps one of the deepest experiences of sublimity available to the modern human mind. Because what Ton 618 represents is not just size, but the ultimate limit. It represents the point where space and time themselves become alien. It represents a place where our knowledge breaks down, and we must admit the limits of human understanding. And in that admission, there is something almost peaceful. It is peaceful to realize that we don't understand everything. It is peaceful to acknowledge that the universe is far stranger and far more wonderful than we can fully grasp. Throughout this night, we have traveled from the familiar the size of a human body, the distance to nearby stars, to the unimaginable the event horizon of Ton 618, a singularity at its center. We have explored how matter can be concentrated to infinite density. We have contemplated how time itself flows differently in the presence of such extreme gravity. We have marveled at the power of quasars, shining with the light of hundreds of trillions of suns. And through it all, we have attempted to understand something that in the truest sense cannot be fully understood by the human mind. And yet we persist, we observe, we calculate, we theorize. We share our findings with one another, building a collective understanding that spans generations. This is perhaps one of the noblest aspects of human civilization, our drive to understand the cosmos, even when that understanding exceeds our grasp. The light from Ton 618 that reaches us carries information from when the universe was young. In that light is encoded the history of one of the most extreme objects ever to exist. That light has traveled across billions of years of cosmic expansion. It has carried its message of cosmic power across the vast darkness between galaxies. And we, small as we are, insignificant as we might feel, have managed to detect that light and interpret its meaning. There is a beauty in that. There is a profundity in that. And as you lie here in the darkness, listening to these words, you are part of that great human endeavor to understand the universe. You are part of a species that looks up at the night sky and asks not just what are those lights, but how far away are they? What are they made of? What can they teach us about the nature of reality? And now, as we draw this journey to a close, let us slow down even further. Let us allow the mind to settle, to relax, to drift gently into a state of peaceful contemplation. Imagine yourself, for a moment, outside the entire observable universe. Imagine that you could float in some abstract space, observing the cosmos from a vantage point impossibly far away. You would see galaxies arranged in vast cosmic structures, filaments and sheets separated by enormous voids. You would see Ton 618 among them, shining brilliantly, one of the brightest objects in this cosmic web. And yet, it would appear as just one point of light among billions of other points. From that impossible vantage point, the entire observable universe would appear as a sphere of finite size, perhaps glowing slightly, alive with countless stars and galaxies and complex structures. This is the scope of creation as we understand it. This is the universe in which we live. And yet, as vast as this is, there is something even more profound to consider. We don't know if this universe is all there is. We don't know if there are other universes beyond the edge of observation. We don't know the true nature of reality at the deepest level. And somehow, impossibly, our minds can contemplate these questions. We can wonder about the infinite. We can imagine, however imperfectly, the unimaginable. Slowly, as you lie here in the darkness, let your breathing settle. Let your mind become calm. The universe has been here for billions of years, and it will continue to exist long after you have fallen asleep tonight. TON 618 has been shining across the cosmos since the universe was young, indifferent to our observation, existing according to the laws of physics that have governed all existence since the beginning of time. And in your contemplation of these cosmic mysteries, you are participating in something profound and beautiful. There is no need to understand everything. There is no need to hold all of this complexity in your mind at once. Simply rest in the knowledge that the universe is vast, that TON 618 is one example of that vastness, and that you, small as you are part of this cosmos. Your consciousness, your ability to wonder and to question, is one of the most remarkable phenomena in the known universe. You are made of the atoms that were forged in the hearts of stars. Your body contains calcium and iron and oxygen, elements created in stellar furnaces billions of years ago. You are, in a very real sense, stardust become conscious, become able to contemplate the stars from which you came. And so, as you prepare to drift off into sleep, know that even in sleep, your mind continues its work. Your brain continues to process, to consolidate memory, to dream. And somewhere in the cosmos, TON 618 continues to spin. Its accretion disk continues to glow. Its jets continue to shine across millions of light years. And the singularity at its center continues to exist, a monument to the extreme places that reality can reach. You are safe here. Your mind can rest. The universe will continue whether you are awake or asleep. And when you awaken, the stars will still be there, waiting to teach you their ancient secrets. Slowly, gently, let your eyelids grow heavy. Let the darkness around you become comfortable. Let the rhythm of your breathing slow and deepen. The universe is infinite, and you are part of it. TON 618 is incomprehensibly vast, and its vastness serves only to remind you of how precious and how remarkable your existence is. Drift now, peacefully, into sleep. The cosmos will still be here in the morning. TON 618 will still be shining across the billions of light years that separate it from us. And you, having journeyed through the universe's deepest mysteries, can rest in the knowledge that you have touched something profound, something real, something that connects you to the largest and most extreme structures in existence. Sleep well and dream of the stars.